Hello students, and welcome to this lesson on properties of logarithms. Our objective today is that we will define and understand the properties of logarithms needed to solve logarithmic equations using notes and practice problems. So first off, let's list our properties of logarithms that we'll be working with today. So given the numbers m, n, and b such that b is not equal to 1, we can make the following statements. If we're talking about the product property of logarithms, then what we're saying is that if I'm given a logarithm such as log base b of m times n, then that will be equivalent to saying log base b of m plus the log base b of n. So we see here that if we have multiplication inside of a logarithm, then we can actually take it out and we can kind of distribute that log onto each piece, and then it becomes an additive property. Additionally, if we have our quotient or division property, we have log base b of m over n. Well, we saw that multiplication became addition. So what do we think that our division is going to become? Well, it's going to become exactly what you think it will be. Log base b of m minus log base b of n. And then finally, let's talk about the power property. So if I have log base b of some number m to the n power, then what I'm going to say is that this is equivalent to n times log base b of m. So those are our three important logarithm properties that we're going to be utilizing today. So let's just talk about why it actually works. So we're going to go through this proof of the product property. And before we get started on that, make sure that you note that this property only works for the same base. So this product rule, this quotient rule, and this power rule only work if you're working in a single base. All right, so let's say that we have log base b of m times n, and that's equal to log base b of m plus log base b of n. How can we prove this? Well, let's go ahead and assign each of these a value. And what I'm going to do is I'm going to assign them a new variable. So I'm going to say that x is equal to log base b of m. And I'm going to say that y is equal to log base b of n. So now I have some variables assigned. So by the definition of a logarithm, I can actually change this, correct? So I know that I can rewrite my logarithm as an exponent. So I can rewrite this as m is equal to b to the x power. Likewise, I can rewrite this as n is equal to b to the y power. If I multiply m times n, then what I get is bx times by. Or in other words, m times n is equal to b of x plus y, or b to the x plus y. Now if I take the logarithm of both sides, I get log base b of m times n is equal to log base b of b to the x plus y power. And what we're going to find is that log base b of some exponent of base b will actually cancel itself out. So we get log base b of m times n is equal to x plus y. But now I know that x plus y, x is log base b of m, and y is log base b of n, so I can say that log base b of m times n is equal to log base b of m plus log base b of n. All right, and then there's one last thing that I want to talk about as far as rules go, and that's our change of base formula. So we've talked about change of base formula before of just saying log of base b of m, right, is equal to the log of m over the log of b. And the reason why we had to do that is because we were trying to go from log base 10 into a log of base b. However, this is not the only situation where you can use change of base. So you can use change of base to go from any base to any other base. So what we can see is that our actual change of base formula given that you're starting in, let's say, in base C. So you could say that the log of base C of m is equal to the log base b of m divided by the log base b of C. So given any pair of bases, you can actually do this. So algebraically, this is also something that you can do. So just be aware of that. We're not necessarily going to use it very often, but just be aware that this might come up, is that this change of base formula is not just used for going from log base b to log base 10. All right, so let's look at some examples. So let's start practicing our actual properties. So I have log base 4 of 32 minus log base 4 of 2. Well, that's going to be our quotient rule, our quotient property, right? So this can be rewritten as log base 4 of 32 divided by 2, or in other words, this is log base 4 of 16, and if we evaluate this, this is 2. All right, let's look at the next one. All right, so we have log base 2, or 6 times the log base 2 of x plus 5 log base 2 of y. So first I'm going to transform this using my power rule. So this will be power and addition. I'm sorry, power and multiplication. So we have log base 2 of x to the 6th power plus log base 2 of y to the 5th power. And again, this is because of our power rule, right? So this multiplication out in front becomes the power of the number inside. And then we have log base 2 of x to the 6th times y to the 5th. And that'll be it, because we can't really evaluate that any further. All right, so log base 5 of 36. So this is going to be practicing our change of base formula. So if I wanted to actually evaluate this in the calculator, remember that's going to be log of 36 divided by the log of 5, and that'll give me my output. And that's going to be approximately 2.227. All right, and finally, we're going to actually take this and we're going to break it down in the opposite direction. So we already have a quotient, right? And we can actually rewrite this as log base 9 of x to the 4th minus log base 9 of 729. All right, and we can further do this by saying 4 times the log of 9 of x, and then minus, and if we take log base 9 of 729, that's going to be 3. So we've evaluated our expression here. All right, and finally I want to talk about using a pH scale. So a pH scale is literally talking about the positive hydrogen in a solution, right? So we're talking about how acidic or how basic something is. And this is something that you guys will see more in chemistry. But the general equation for pH is going to be pH is equal to the negative log of the concentration of positive hydrogen atoms. And the reason that we use this log, this negative log, is because our concentrations are going to be extremely small. Like the quantities of these is extraordinary. So if we're taking, say, trying to find the pH of something, let's say ammonia, right? And ammonia is going to be equal to 6.3 times 10 to the negative fifth. That is the concentration of positive hydrogen atoms in ammonia. So what the pH value gives us is a nice scale to be able to look at it versus other items. So if we're trying to calculate the pH of this value, we're literally just plugging it in. So it's going to be the negative log of this number, 6.3 times 10 to the negative 10th power. I'm sorry, to the negative 5th power. And we can actually break this down a little bit further. So we have negative log of 6.3 plus the log. And what's great about this is that this creates a little bit easier of an evaluation process for us. So if we've got the log of 10 to the negative 5th power, well, log is already base 10. So we can just say minus 5 here, and then the logarithm of 6.3 is going to be approximately 0.799 minus 5. And then that'll be all to the negative power. So our actual pH value that we get is going to be 5 minus 7, or 0.799. And we get that this is going to be approximately, I'm just going to approximate it as 4.2. So that's our actual pH value there. So that's not something that's too important to us as mathematicians, but as scientists, that might be important to us later when we go to chemistry. All right, so your reflection today is, how are the product rules for exponents and the product rules for logarithms related? How do they work with each other, and how might one be used to develop the other? Then your assignment for today is that you're going to do 7-6 properties of logarithms. If you have any questions, let me know, and have a wonderful day. Goodbye.